Stars, the celestial furnaces that illuminate the universe, are not eternal. They are born, they live, and they die. A star's life is a balance between gravity and nuclear fusion. For millions or billions of years, these forces create the energy that makes a star shine. However, even the most massive stars have a finite amount of fuel. As a star ages, it exhausts its hydrogen, disrupting the equilibrium. This causes the star to swell, shrink, and change color. More massive stars explode as supernovae, among the most energetic events in the universe. Gravity, the invisible force that governs the cosmos, plays a pivotal role in the life and death of stars. It draws together vast clouds of gas and dust, igniting the nuclear fires that give birth to stars. As a star ages, gravity's grip tightens. The star's core begins to contract. In massive stars, this triggers a supernova explosion. The remnants, neutron stars, and black holes are among the densest objects in the universe. Gravity binds stars and galaxies, shaping the cosmos. While the death of a star may seem like the end, there are instances where these celestial objects can experience a resurgence, a brief return to brilliance. This phenomenon, often unexpected and intriguing, is a testament to the power of gravity and the complex interactions that can occur in the universe. Dead stars, particularly white dwarfs and neutron stars, can reignite under certain conditions, emitting bursts of light and energy that ripple across the cosmos. This reawakening is not a sign of life, but rather a consequence of their extreme environments and the gravitational pull they exert on their surroundings. These stellar afterglows, often observed as novae or supernovae, provide astronomers with valuable insights into the processes that govern stellar evolution and the extreme physics at play in the universe. They are a reminder that even in death, stars can continue to influence the cosmos around them. Throughout history, astronomers have observed numerous instances of dead stars seemingly coming back to life. These events, often visible to the naked eye, have captivated observers and fueled scientific inquiry. One such example is the recurrent Nova Rs Ophiuchi, a binary star system located about 5,000 light-years from Earth. Rs Ophiuchi consists of a white dwarf and a red giant star locked in a close orbit. The white dwarf, despite being a stellar remnant, periodically erupts, becoming bright enough to be visible without a telescope. These eruptions are caused by the white dwarf's intense gravity pulling material from its companion star. As this material accumulates on the white dwarf's surface, it eventually reaches a critical temperature and pressure, triggering a thermonuclear explosion. Another example is the supernova SN 1987A, which occurred in the Large Magellanic Cloud, a nearby galaxy. This supernova, one of the brightest in centuries, was caused by the collapse of a massive star. Even decades later, astronomers continue to observe the expanding debris cloud, studying its composition and evolution to gain a deeper understanding of supernova and the processes that drive them. Section 5. Unveiling the mystery, the science behind stellar afterglows. The phenomenon of dead stars shining again is a testament to the extreme conditions that can exist in the universe. It is a realm where gravity reigns supreme, distorting space and time and, well, pushing the limits of physics as we know it. The key to understanding these stellar afterglows lies in the concept of accretion. Accretion is the process by which an object with a strong gravitational pull, such as a white dwarf or a neutron star, draws in material from its surroundings. This material, often gas and dust from a nearby companion star, spirals inward towards the compact object, forming an accretion disk. As the material falls closer to the object's surface, it gains speed and heats up, emitting intense radiation. In some cases, the accreted material can trigger thermonuclear reactions on the surface of the white dwarf, leading to a nova explosion. In other cases, the material can accumulate on the surface of a neutron star, eventually causing it to collapse further, potentially forming a black hole. Section 6. White dwarfs and their companions, a dance of accretion. White dwarfs, the remnants of stars like our Sun, are incredibly dense objects, packing the mass of the Sun into a volume roughly the size of Earth. Their gravity is so strong that a teaspoonful of white dwarf material would weigh several tons on Earth. When a white dwarf exists in a binary system with a companion star, its gravity can pull material from its companion's outer layers. This material, primarily hydrogen and helium, forms an accretion disk around the white dwarf. As the material spirals inward, it heats up, eventually reaching temperatures high enough to trigger thermonuclear reactions. These reactions, occurring on the white dwarf's surface, release a tremendous amount of energy, causing the white dwarf to brighten dramatically. This brightening, known as a nova, can last for weeks or even months before fading back to its original luminosity. Novae are not destructive events. The white dwarf remains intact, and the cycle of accretion and eruption can repeat over thousands of years. Section 7. Neutron stars, the ultimate gravity wells. Neutron stars are the collapsed cores of massive stars that have exploded as supernovae. They are among the densest objects in the universe, with a mass greater than the Sun compressed into a sphere only a few miles across. The gravity on a neutron star is so intense that atoms are crushed, forcing electrons and protons to combine and form neutrons. This extreme density gives neutron stars some unique properties. For example, they rotate incredibly fast, often hundreds of times per second, and emit powerful beams of radiation from their poles. Like white dwarfs, neutron stars can also accrete material from companion stars. However, the consequences of accretion onto a neutron star can be even more dramatic. The intense gravity can cause the accreted material to undergo nuclear fusion, releasing bursts of X-rays and gamma rays. In some cases, the accretion can cause the neutron star to spin faster, emitting pulses of radiation that sweep across the sky like a lighthouse beam. These objects, known as pulsars, are some of the most precise timekeepers in the universe. Black holes are perhaps the most enigmatic objects in the universe. They are regions of space-time where gravity is so strong that nothing, not even light, can escape. Black holes form when massive stars collapse at the end of their lives, creating objects so dense that they warp the fabric of space-time. While black holes themselves are invisible, their presence can be inferred by their effects on surrounding matter. As material falls into a black hole, it forms an accretion disk, just like around white dwarfs and neutron stars. However, the material falling into a black hole is heated to such extreme temperatures that it emits intense radiation, including X-rays and gamma rays. These emissions can be detected by telescopes, allowing astronomers to study black holes and their properties. The study of black holes provides insights into the most extreme environments in the universe and the nature of gravity itself. The death of a star is not the end, but rather a transformation, a recycling of matter and energy that contributes to the ongoing evolution of the universe. The material ejected during supernova explosions, for example, enriches the interstellar medium with heavy elements, the building blocks of planets and life. These elements, forged in the hearts of stars, are scattered across the cosmos, seeding new generations of stars and planetary systems. Our own solar system, for example, formed from a cloud of gas and dust that was enriched by the remnants of previous generations of stars. In this sense, stars are not isolated objects but rather interconnected parts of a vast cosmic web. Their lives and deaths contribute to the ongoing cycle of stellar evolution, ensuring that the universe remains a dynamic and ever-changing place. The study of stellar afterglows, from novae to supernovae, provides astronomers with valuable insights into the universe and its workings. These events, often brief but incredibly luminous, offer glimpses into the extreme physics at play in the cosmos. By observing the light from these events, astronomers can study the composition of stars, the processes that drive stellar evolution, and the properties of exotic objects like neutron stars and black holes. For example, the study of supernovae has allowed astronomers to measure the expansion rate of the universe and to probe the nature of dark energy, a mysterious force that is accelerating the universe's expansion. Furthermore, the study of stellar afterglows helps us to understand the origins of the elements that make up our world and ourselves. The carbon in our bodies, the oxygen we breathe, and the iron in our blood were all forged in the hearts of stars that lived and died long ago. The universe is not a static and unchanging place, but rather a dynamic and ever-evolving tapestry of life, death, and rebirth. Stars are born, they live, and they die, enriching the cosmos with the building blocks of future generations of stars and planets. The phenomenon of dead stars shining again, a testament to the power of gravity and the intricate interplay of cosmic forces, reminds us that even in the vastness of space, nothing is truly lost. Instead, matter and energy are constantly being transformed, recycled, and repurposed, ensuring that the universe remains a vibrant and ever-changing place. As we continue to explore the cosmos, we can expect to uncover even more wonders, revealing the secrets of stellar evolution and the interconnectedness of all things in the universe. The study of dead stars shining again is just one piece of the puzzle, a glimpse into the grand cosmic cycle that connects us all.